Albert Einstein revolutionized our understanding of the universe with his theories of relativity. Before Einstein, the universe was seen as a giant clockwork mechanism. Einstein shattered these views, revealing a universe far stranger and more wondrous. His theories profoundly impacted our understanding of the cosmos and paved the way for countless technological advancements. Prepare to embark on a journey that will challenge your perceptions and illuminate the profound beauty of Einstein's universe. Imagine you're on a train, traveling at a constant speed. You toss a ball straight up in the air. From your perspective, the ball goes straight up and down. Now imagine someone on the ground watching the same event. They see the ball travel in a parabolic arc. This illustrates a fundamental principle of Einstein's special relativity: motion is relative. One key insight is that there is no absolute frame of reference. This means the laws of physics are the same for all observers in uniform motion. According to classical physics, the observer on the ground should measure the speed of light to be faster. This is because in classical mechanics, velocities are additive. If you are moving towards a light source, you would expect to measure the light's speed as the sum of your speed and the speed of light. Conversely, if you are moving away, you would expect to measure it as the difference. However, Einstein postulated that the speed of light in a vacuum is constant for all observers, regardless of their motion relative to the light source. This revolutionary idea forms the cornerstone of his theory of relativity. It means that no matter how fast you are moving, whether towards or away from the light source, you will always measure the speed of light to be the same. If the speed of light is constant, then time itself must slow down for the observer on the train. This phenomenon is known as time dilation. Imagine you are on a train moving close to the speed of light. To an observer on the ground, your clock would appear to tick more slowly than their own. This is because, to keep the speed of light constant, time must adjust. This concept of time dilation has been experimentally verified. Scientists have used highly accurate atomic clocks to demonstrate that time indeed slows down for objects moving at high speeds. For instance, atomic clocks on fast-moving aircraft or satellites show a slight difference in time compared to those on the ground. The speed of light sets a cosmic speed limit, a barrier that nothing can surpass. This limit is approximately 299,792 kilometers per second, or about 186,282 miles per second. No matter how much energy you put into accelerating an object, it can never reach or exceed this speed. This influences our understanding of the cosmos and our ability to travel vast distances. The finite speed of light means that we see distant objects as they were in the past, not as they are now. It also imposes significant challenges for interstellar travel, as reaching even the nearest stars would take many years, if not centuries, with our current technology. Time dilation becomes more pronounced as an object approaches the speed of light. This phenomenon, predicted by Einstein's theory of relativity, fundamentally alters our perception of time and space. Imagine a spaceship traveling at a significant fraction of the speed of light. As it accelerates, the effects of time dilation become increasingly significant. The astronauts aboard this high-speed vessel would experience time passing slower compared to people on Earth. For them, a journey that seems to last only a few years might equate to decades or even centuries on Earth. This concept has practical implications, such as in the Global Positioning System, GPS. The satellites orbiting our planet are moving at high speeds and are also further from the gravitational pull of the Earth, both of which affect the passage of time. GPS satellites carry atomic clocks that run slightly slower than clocks on Earth due to time dilation. Without accounting for these differences, the GPS system would quickly become inaccurate, leading to errors in positioning and navigation. Engineers and scientists must constantly adjust the satellite clocks to ensure GPS accuracy. This meticulous calibration is crucial for the system to provide precise location data, which is essential for everything from navigation to telecommunications. Time dilation challenges our understanding of time as a rigid and unchanging entity. It forces us to reconsider our notions of past, present, and future, and how they are interconnected. It reveals time as a fluid and relative concept, linked to motion and the observer's frame of reference. This understanding opens up new possibilities in physics and cosmology, suggesting that our universe is far more complex and interconnected than we ever imagined. Perhaps the most famous equation in physics, EMC2, reveals a profound connection between energy and mass. Before Einstein, energy and mass were seen as separate entities. EC 2 demonstrates that mass is a concentrated form of energy. This equation has had a profound impact on our understanding of the universe, particularly in nuclear physics and cosmology. It highlights the elegant simplicity with which the universe operates at its most fundamental level. One of the most intriguing thought experiments in special relativity is the twin paradox. Imagine identical twins, Alice and Bob. Alice embarks on a high-speed space journey while Bob remains on Earth. When Alice returns, she will have aged less than Bob due to time dilation. The twin paradox arises from the seemingly symmetrical nature of special relativity. However, Alice's frame of reference is non-inertial due to acceleration. Therefore, special relativity applies differently to Alice and Bob. The twin paradox reinforces the principles of special relativity and highlights the profound consequences of time dilation. 10 years after special relativity, Einstein completed his masterpiece, general relativity. General relativity extends these principles to include acceleration and gravity. Einstein's key insight was that gravity is a manifestation of the curvature of space-time. Imagine a bowling ball on a trampoline, causing it to sag. A marble's path curves as it approaches the bowling ball due to the trampoline's curvature. Similarly, massive objects warp space-time, creating gravity. This curvature affects the flow of time, known as gravitational time dilation. General relativity provides a more accurate description of gravity, particularly in strong gravitational fields. To further grasp curved space-time, let's delve deeper into the trampoline analogy. A heavier bowling ball creates a steeper curvature on the trampoline. Similarly, objects with more mass cause greater curvature of space-time. This explains why massive objects exert stronger gravitational pull. Objects with higher velocities are less affected by space-time curvature. The trampoline analogy helps visualize gravity as a consequence of space-time geometry. Massive objects distort space-time, and other objects follow this curvature. One fascinating prediction of general relativity is gravitational lensing. Gravity warps space-time, affecting the paths of light. Imagine a distant galaxy behind a massive cluster of galaxies. Light from the distant galaxy is bent by the warped space-time around the cluster. This bending acts like a lens, magnifying and distorting the distant galaxy's image. Gravitational lensing provides strong evidence for general relativity and is a powerful tool in astronomy. Einstein's theories of relativity have had a profound impact on technology. His groundbreaking work has paved the way for numerous advancements that we often take for granted in our daily lives. One notable example is the Global Positioning System, GPS. This system, which we use for navigation in our cars, phones, and even for tracking packages, is a direct application of Einstein's theories. GPS relies on a network of satellites orbiting the Earth, each equipped with highly precise atomic clocks. These clocks are crucial because they are affected by both special and general relativity. Time dilation, a concept predicted by Einstein, causes the clocks on these satellites to run slightly slower than those on Earth. This difference, though minuscule, can lead to significant errors if not corrected. Engineers continuously monitor and adjust the satellite clocks to ensure the accuracy of the GPS system. This meticulous process ensures that the system remains reliable for all its users. Without these precise corrections, GPS systems would quickly become inaccurate, leading to errors in navigation and timing that could have widespread consequences. Beyond GPS, Einstein's theories have influenced a wide range of technologies. For instance, particle accelerators, which are used in cutting-edge research and medical treatments, rely heavily on his work. These accelerators study the behavior of particles at incredibly high speeds, providing insights into the fundamental nature of matter. The famous equation E=mc², which describes the relationship between energy and mass, is central to this research. Additionally, nuclear power, which provides a significant portion of the world's energy, is another area where Einstein's theories are applied. Understanding the energy released in nuclear reactions is crucial for the safe and efficient operation of these plants. Even in the field of medicine, technologies such as MRI scanners are based on principles derived from Einstein's work. These machines allow doctors to see inside the human body with incredible detail, aiding in diagnosis and treatment. As we continue to explore the frontiers of science and technology, Einstein's theories remain a cornerstone. From quantum computing to space exploration, his legacy endures, driving innovation and expanding our understanding of the universe. Albert Einstein's theories of relativity revolutionized our understanding of space, time, and gravity. They replaced the classical Newtonian view with a more elegant and accurate description of the universe. His theories have led to technological advancements that have transformed our world. Einstein's legacy continues to inspire and guide our exploration of the universe. The journey that began with a simple question about light has revealed a universe far stranger and more wondrous than we could have ever imagined.